me because I'll forget. I know it. All right, so we're going to go back over some different graph characteristics that give us information on the polynomials. So if we're looking at this one, and it asks you for degree. So based on what we have there and what we're seeing, what could be the degree, like the lowest possible degree for this polynomial based on the information that's here? Well, let's just say whether it's, all we're looking for here, let's just say odd or even. Do we know if this is an odd or even degree? Which one would it be? 50-50 shot, but odd, right? Because odd is opposite directions. See how like the right end is going up, the left end's going down. Odd, opposite. If this were even, both ends would be going either up or down, the same. So we know for a fact it has to be odd. And then kind of with that, what would be the leading coefficient? Positive or negative? To review that, you can look at the end behavior up there, like that little diagram, right? The leading coefficient, positive or negative. But with odd, and this is something I think I said before, but again, I'll repeat it if I didn't. When you think of a line, right? Lines are first degree polynomials, so they're odd polynomials. So if you could kind of think of it in terms of a line, and the slope of the line, that's the leading coefficient, right? Whatever the slope is the leading coefficient in a linear, slope-intercept equation. So would this one have a positive slope or a negative slope? Like this first one. Positive, right? Because it goes like uphill. So if you look at this graph, if you go from like this end to that end, this kind of like draw even just an imaginary line in your head, that would have a positive slope, right? If you go from this end up to that end. So it kind of is like the same thing. Now if it was reversed and I went from this end down to that end, it would be like a negative slope. So odd, once you determine it's odd, you can think about, well, if I draw a line from one end to the other, would it have a positive or a negative slope? And that's the same thing as the leading coefficient. So this one would have a positive leading coefficient. Number of real zeros. Now, it talks about real zeros here versus imaginary. How can I tell from a graph if it's a real zero? Like, what's the difference between real and imaginary in terms of a graph? If you have a, so if you have a graph that looks like a quadratic, right? A parabola, and it looks like this. It doesn't have any real roots because it doesn't cross the x-axis. It's still going to have two imaginary solutions, but real roots are when you cross the x. So like this one would have two real roots. This one has two imaginary roots because it doesn't cross the x. We don't know what they are. So here, if we just count x-intercepts, that's the real roots. So we got, 1, 2, 3, 4, 5. There's 5 real roots. Now it could have more, could have ones we don't see maybe. These are, x-intercepts basically. Right end behavior. So if we're looking at this, the right end is over here, right? The right side of the graph. The right side of the graph goes up towards infinity. The left side of the graph goes down towards negative infinity. And that's all these questions are asking. Which way is that right arrow pointing? It's up towards positive infinity, or right end pointing. The left end is continuing down towards negative infinity. Max number of turns, you just count them, you know. So you have 1, 2, 3, 4 turns. And that, now if we're thinking about what the degree of this is as far as a number, besides it just being odd, if I have 4 turns, it's probably a 5th degree, right? It's at least a 5th degree. And it can't be more than that, or it can't be less than that. Like, it's not like this can be a 3rd degree because it has 4 turns. Turns versus degree, minimum degree, is just, the difference is 1. You either add 1 to the turns or subtract 1 from the degree to find the turns. Domain and range is something we haven't talked about, but you did a lot in Algebra 2. The nice part about an odd polynomial, the answer to both of these is the same, and it's just all real numbers. Because it's continuous left to right from negative to positive infinity, and it's continuous up and down because both ends go up or down. So this one is just going to be, you know, from negative to positive infinity for range, negative to positive infinity for domain. This is true for all odd polynomials. So you don't really have to remember much, but if you know that it's odd, it's all real for both, right? So that's easy enough. The next unit, 1b, we start to look at some that aren't going to be, like there'll be restrictions on the domain and stuff, but for these, you know, range and domain are both all real numbers if it's odd, right? So take a second and look at this. Try to fill in maybe what you know. If you're not sure, just leave it for a second and we'll go over it. But you know, this will be kind of a test to see what you know for yourself. If you knew them, they're pretty quick, so let's just kind of look at them here. Is the degree of this polynomial even or odd? Is it an even or odd number? It's even, right? Because both ends go up. If both ends are going in the same direction, it's got to be an even. Is the leading coefficient positive or negative? Positive, right? They both go up. Like if you look over there at that chart up in the corner of the board, even positive, both ends go up. Even negative, both ends go down, right? And then odds are opposite directions. So we know that it has to be positive. What are the real zeros of the polynomial? Like the real housewives of polynomials here. So we got -5, right? That's a real value because it goes through the x-axis. We got 0. So -5, 0, and 4. Those are our real zeros. What is the smallest possible degree that this polynomial could be? Like, yeah, like we know it's got to be an even number, right? So the smallest even number is 2, but it's got to be more than that. And then we can count the turns, right? And I see some people holding up 4 fingers. So we got 1, 2, 3 turns. Add 1, you got 4. So it could be the smallest it could be is a 4th degree. Where is there a double root? A double root. So remember, the bounce is a double root. So it's 0 at 0, 0. We could just say at 0. That's a double root. Point of tangency. We'll talk more about that in a second, but if you remember from geometry, which I'm assuming 100% of you don't, but since it was circles, and that was probably right about the time for you guys that you kind of got stopped for coronavirus or something, like that was 2 years ago. But a tangent, when you have a line that's a tangent to a circle, it means it comes right up on it and touches it at like one spot, right? They only touch at one spot rather than like a line that just goes straight through it, right? A tangent line is tangent to it, and by using the name of the definition is kind of bad, but it just means it goes right up against it, but it doesn't go through it. There's just like one spot where it touches. So that's why a double root is also called a tangent, a point of tangency, because it goes right up against it, just touches it at that spot, and then goes down, versus going through, right? So that's what a point of tangency is. It's the same as a double root when you're considering it on a graph. Domain is all real numbers. Again, that's the answer for every polynomial, all real numbers. Next unit we'll get some that are different domains. The range for an even polynomial though is not going to be all real. Odd it is. Like this one's an odd, we can just go down here and actually fill in domain and range, because it doesn't, if it's an odd, the domain and the range are all real. But this one, what would be the range of this second one? Anybody? Remember how range works. It's your lowest y value to the highest. Our lowest y value is right here, right? It's at -6. So this graph doesn't go any lower than that. So your range would be from -6 to infinity. But I'm going to use a bracket instead of a parentheses. Range for these is always going to have a bracket on the one end where it's like not infinity or negative infinity, because it actually equals -6 at this spot. So that's why we use a bracket there. It can never equal infinity or negative infinity. That's why we always use parentheses for them, because like infinity is like a constantly moving thing, right? So you can never actually equal it, because it's always like, well, let's go one more further. So range should always have the bracket, and it's whatever either the lowest point is, or if it's, you know, if you get one like this, it would be like negative infinity to whatever this would be. All right, next one. So here we have an even or odd. It's got to be odd, right? Odd opposite. So fairly opposite or fairly odd ends. Is the leading coefficient positive or negative? So again, if we kind of just do that idea of, well, let's see if I draw like an imaginary line from one end to the other, would it go up or down? Would it have a positive or negative slope? This would be negative, right? If I draw a line through there, so it'd be a negative. What are the real zeros? We got -3, looks like -1, 0, and 2. Smallest possible degree of the polynomial. Again, this is something you guys, some of you struggled with a bit on that first quiz. If you can count terms, you just add 1, and that's the degree, or it's like the smallest possible degree. So we have 1, 2, 3, 4 terms, so that would mean that the smallest possible degree would be 5th. Like we already know it's got to be an odd number, so it couldn't be the same as the terms, because remember we're looking for an odd degree. So it's 1 more, and you have 4 terms, and that gives you the 5th degree polynomial. So terms plus 1, right? And then where's the double root or point of tangency at this one? Remember the double roots that bounce. So here we got a double root at 2, right? Because it kind of comes up, bounces off, and keeps going down. Any questions on any of that before we kind of move on? Because we do have a couple new things to kind of add. we haven't really done yet. All right. So let's just, this is just some function f prime. This is its graph. So if you remember algebra 2, or from it, you did a lot with increasing and decreasing, right? We always talked about like what interval are we increasing and decreasing. Increasing means, like, if you think of this as like a roller coaster, right? Starts here, finishes here. Increasing is when you're gonna go up, right? Like here's when you like first start out on the roller coaster, you're going up, 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 and then right here it switches over and starts decreasing, right? And then you get down here at the bottom and it changes over and starts increasing again, and then it starts decreasing. So when it's asking you for an interval, it's saying like from where to where is it happening. So like in this case, and it's never going to be the y value unless it says specifically something about that, but when it's looking for, where is it increasing, if we go from, and they're going to be in like two sections here, but like if you think about it like this, like that's about, it stops increasing like right here, right? From here to here, or from here to about, let's just call it 1 to make it easy, it's increasing. So from like 0 to 1, it would be an increasing interval. When you're putting increasing or decreasing intervals, you have to make sure to, it's always going to be parentheses, because when you hit this point 1, or it's actually a little after 1, but we'll just call it 1, it's doing nothing right here. Like it's neither increasing or decreasing at this point. It's like a turnover point. So when it hits the peak, it's no longer increasing and it hasn't started decreasing yet, and then it starts decreasing after. So let's just say from like 1 to 2. What's up? Oh, you can grab those papers. What's that? No, is there, just grab an open seat. I don't, like it didn't switch, but so here's this one. If we're looking at this next section, right? And again, we just kind of called it 1 for this one, and let's just call this one 2 to kind of make the numbers easier. So from like 1 to 2, it's a decreasing interval. Remember, we're saying from 1 to 2, you always read it left to right, and during that, over that interval, it's decreasing. So that would be a decreasing interval, 1 to 2. And then if we look here on the paper, like, I guess we'll call this like 2.75. I need to make a better graph on this. So from like 2, really about 2.1, I guess, but from 2 to 2.75, it's increasing again. And then we'll say from 2.75 to 3, it's decreasing. And notice along this graph in particular, it's either doing one thing or the other, right? From 0 to 1, increasing, 1 to 2, decreasing, 2 to 2.75, increasing again, and then 2.75 to 3, decreasing. So when we're talking about an interval for increasing or decreasing, you're always going like left to right. I don't care how high it goes or low it goes, we're just wanting to see where it kind of changes over from one thing to another, or what it's doing over a section of the graph. All right, so on approximately what interval is f prime, this graph, greater than 0? What is, in terms of a graph, what's greater than 0, like visually? Is it above the x-axis or below the x-axis? Above, right? That's greater than. So if we look in here, this whole section is increasing. This is all a positive section here. The two papers are over there. Is that what you're looking for? Like on that desk? It's on the back page of the one with the 3 sections on it. Caught me sleeping. All right, so the positive sections are like here, right? These are positive parts. This would be like a negative part. So on what interval is it greater than 0? From 0 to, I don't know, this would be like, I guess, 1.75. Let's just call this 1.75 because we're just estimating. So from 0 to about 1.75, it's all positive. And then it's negative from 1.75 to, I don't know, 2.5 maybe. Because below 0 is when it's below the x-axis, or less than 0. And what do we call it? Let's just, I don't know, 2.5. And then it increases again from 2.5 to 3. It's positive from 2.5 to 3. So that would be 2 positive intervals and 1 negative. Okay. And again, just like here, this graph, it's either positive or negative. So like these kind of connect each other. 0 to 1.75, 1.75 to 2.5, 2.5 to 3. It's something. It's either it's positive or negative everywhere on here. What are the approximate zeros? I don't know, we're just they're the same things we just used though. If you notice, it's like these values, right? 0. So at the zeros, it changes over from positive to negative. 1.75, and then we got one at 2.5. At approximately what values of x does this have a local maximum? So again, it's asking you about where it's happening, not what it is. So like here's a max, right? So our max is taking place at, well, we already called this 1 where it stopped increasing, so let's just stick with that number, I guess, even though it's maybe a little bit past 1. But it's going to be these same numbers where it changes over from increasing to decreasing. So we have a maximum at 1, and then our other maximum is here at like 2.75. And notice those are the 2 values where it stopped increasing, because those are like our peak points. And then where it stopped decreasing at whatever we call this, 2 point, let's see. Oh, I guess we just called that 2, right? Because at 2, it's down here. So our minimum would be at 2. There's only one minimum. But it's these same values repeated, right? 0 to 1 is increasing, so that hits your peak. 1 to 2 is decreasing, and that's where you hit your minimum. And then 2 to 2.75 is where we hit that other maximum. So it's like these n values. All right, so this is somewhat of a new concept as far as calling it concave up or concave down. If you remember from, and again, I'm trying to like reference geometry, and maybe you do or don't remember, but if you had like a polygon like this, I'm just trying to make one up that sort of fits it. Like that, right? Maybe that would be called like concave polygon, because it's caved in, right? Or you have like this cave opening here. And when you're referring to a graph, like this would be considered concave down. It's kind of like how the curve is opening. So like this one kind of opens down. This would be concave up. And then this one would be concave down again. Now, when we're considering like the intervals though, of where it's happening, so this is down obviously, right? But if I'm going along the graph and I get to like here, am I in a concave up or concave down spot? You know what I'm saying? Like at some point it changes over where it stops doing one thing and starts doing another. So it's not like this whole U here is concave down, because as we get to like right here about the halfway point, it sort of changes over, right? So now we're on like an upside. And then here, this is, you know, this section is down, but like where does it start happening and stop being up? It would be there. So the changeover is always in the middle. And what you call that is, it's called an inflection point. So it's an inflection point, and then this would be an inflection point. And an inflection point is, it's where a change in concavity happens. Meaning it's like where it changes over from being one thing to the other. So like this is an inflection point. If you guys remember, and you probably don't, it just stood out to me because I had, you know, used the term a lot in pre-calc, when President Biden was making like his like election night like acceptance speech and everything, he talked about the country being at an inflection point, or the election being an inflection point for the country, right? Because an inflection point is when it like stops doing one thing and starts doing another. It's a change. And it stood out to me. I'm like, well, that's pretty cool. He's using a math term there in the speech. And it made sense because it's like, you know, it did, you know, signify a big change for the country at that moment. All right. Anyway, so I thought that was cool that he said inflection point, but you know, it has dual meanings, but it kind of makes sense here. Like it changes from going up to down, down to up, and that's what an inflection point is. All right. So if we're looking at this one, and again, we're kind of estimating it, right? Approximately what interval is it happening, or at approximately what interval is this concave up? So this would be an up section right here, right? But where does it stop being up and start being down is about, you know, in the middle, right? Because right where it kind of starts to curve. So from like 0 to, let's just call it 0.5, it would be up. And again, we're using parentheses here because at the moment it's changing, it's like nothing. It's neither up, concave up or down. So the changeover point, you know, we use parentheses on those. So the next spot that it maybe changes over, because here it's going down, but it starts going up, you know, again, you just kind of estimate about the middle of the graph. And here it almost feels like where it crosses the X is sort of the middle, right? So we'll just call it whatever that 0 was, 1.75, I guess. Because, you know, it's going down, and then at this point about, it changes over and starts going up. So that would be, sorry, our down interval would be 0.5 to 1.75. And then again, it's kind of going to be connecting. So at 1.75, that's an up interval. And then up till about, I don't know, 2.5, it would be going up again. And then, you know, 2.5 to 3, it's all going concave down. Because there's no like extra curve here. It just seems like it's all going down. You can't see what a halfway point is. All right, so we repeat a lot of the same numbers because, you know, changes in increasing and decreasing are the same as like the maximum and minimum. These aren't really repeated numbers, but they're like in the middle of the other number. And then at approximately what value does x, what values of x, again, we're only talking about x values, not y values, does this have an inflection point? And this is where we're using these same numbers, because remember, these were inflection points where it changed from being concave up to concave down was at 0.5. And then where did it change from going down to up? That was at 1.75. And then it starts going up again, concave up again at 1.75, and it stops at 2.5. So these inflection points are where it stops doing one thing, starts doing another. And I guess 2.5 was our last one. So those three spots would be inflection points, right? A lot of vocabulary there. I'm kind of just reading into the graph. Let me stop it at that spot because this is already approaching being a long video.